Yes. Okay, guys, welcome to my new video lecture that is exercise. After that exercise, I will not going to do other exercise maybe because I had already told you guys how to do the problem, and in this video we will know some of the new things. Okay, let's go to the lecture. Okay, here I had written some problem. Consider a steady 1D heat conduction in a large plane wall of thickness L and constant thermal conductivity K with no heat generation. That is, heat generation E generation is 0. No heat generation. Obtain expression for the variation of temperature within the wall of the following belonging pair boundary condition. For boundary, I had given a boundary condition. Now what I have to find out? I have to find out the solution, guys. Okay, what is the temperature distribution in the wall and the heat conduction also maybe. Okay, now first one is that it is given in the form of heat flux, guys. Minus k dt by dx at x equal to 0. Dt by it is the t is the function of x, guys. You have to know that x is equals to 0 means at x equal to 0 the heat flux q naught equal to 40 watt per centimeter square. And T0, another one is a temperature boundary condition at x equal to 0, again given to, that is T naught equal to 15 degrees Celsius. At x equal to 0, the temperature flux is given and the temperature is given. And another, for this section we will find out the what is dt square by dx square and other thing. For B, for in B, minus the flux is given minus k dt by at x equal to 0 flux is given 40 watt meter square, and at x equal to L the flux is given minus 25 watt per centimeter square. In a third boundary condition is minus k dt by x equal to 0. What is the temperature distribution? What is the heat flux? 40 watt per centimeter square. Or in the distance at x equal to L, like this. Okay, this is the x. Okay, this is the y at x equal to 0. This is the x equal to 0 and this is the x equal to L. The heat flux at this point it is given by 40 watt per centimeter square. 40 watt per centimeter square. Now from equation 1, okay, from equation, not equation 1, we will here solution. How we will solve it? The heat conduction equation is, we know that the heat conduction equation is d square t by dx square equal to 0. By integrating which we get general solution. That what we get? The general solution is tx c1 x plus c2. This is equation 1. Now let's move to the first A boundary condition. We will solve for the boundary condition of A. What we will get, we will see. Okay, guys. I had done in a very detailed way. Don't worry, guys. It's a very convenient way, and you can know these things. In this case, both boundary conditions are specified at the same boundary at x equal to 0. Okay, guys. If you have written it, this is x equal to 0, and this is also x equal to 0. Written, the boundary condition are given at x equal to 0. Both the boundary condition are given for the x equal to 0. Okay, this is the thing. And no boundary condition is specified at the other boundary condition, that is if this is an x equal to 0 and there is no boundary condition is defined. Okay, only two boundary conditions are given, those are defined on the x equal to 0. Okay, now we know that dt by dx equal to c1, and after that we will solve. After solving we will get this one. Okay, guys, no need to problem, no need any. Okay, and another thing is that before that we have solved that. If you solve this one, okay, I will just write in a bracket what we have done. If you integrate it in first, what we will get? dt by dx equal to c1. What is this, guys? This is the temperature gradient. Okay, temperature gradient is equal to the c1. This same thing is written here. What? Noting that dt by dx equal to c1, no need to worry about it. this is the temperature gradient we will get equal to C1 in every section. Okay guys, the application of boundary condition given, we had given the boundary condition at x equal to 0. Two boundary condition, one is flux, another one is heat. Okay, we will try for the flux. Okay, minus k dt by dx. What is dt by dx? dt by dx is equal to c1. Okay, dt by dx, this is the heat flux at x equal to 0, that is q naught. Okay, here is the rate of heat flux. Okay, it has given minus k c1. Okay, c1, what is c1? I already told you guys, when you take integration, we will get the heat temperature gradient will be equal to the c1. Okay, now then we will, after that we will so you get c1, and c1 is written here, and c1 equal to, we don't know this, we have to find out this arbitrary constant. So c1 will be here, and it will become what, this minus sign will go here, minus k q naught q heat flux, rate of heat flux, divided by k thermal conductivity. And another one, what we had given, the temperature at x equal to 0. So what we'll get, and t0, we will put 0 here, c1. What from the equation first, what we have given, tx, the temperature function is c1x plus c2. Okay, we will put the value in here. What we have given, that is t0, the boundary condition at x equal to 0 equal to c1 into x. In place of x we will put 0 because x value is 0, plus c1 c2. Okay, now it becomes 0, and c2 will be equal to 15 degrees Celsius, which is the value of t naught value is the temperature at x equal to 0. Okay, we had get the both c1 because we had given the q naught, rate of heat flux at x equal to 0. What is this? 40 watt per meter square, and we have to do, after dividing it by the k, we will get the c1 value. Okay, now what we have, tx equal to c1x plus c2. From this section we had find out the c1, and from this section we had find out the c2. Okay, sorry guys, from this point we had find out the c1, and from this section, this boundary condition, the temperature boundary condition, we have to find out this c2, and we will put this value in this section, and we will get this solution, minus q, c1 value is q naught, the rate of heat flux upon my thermal conductivity, into x is the x. Okay, this is the x, plus c2 value is ct naught. Okay, now solve this. Now we get the temperature function, and we can find out. Now we have a function of tx, and we can find out the temperature at any point. Okay guys, now let's move to the b. In this section, what happens, the boundary condition, that is heat flux boundary condition, are given to the at x equal to 0 and x equal to L. Okay, now you have to just think about it, and just don't forget about it. Okay guys, it will play a very important role. Okay, you will know the very new thing here. What that thing, I will tell you guys. For heat conduction equation, we know that the heat conduction equation, d square t by dx square equal to 0, equation 1. dt by dx, if you integrate it with respect to x, you will get dt by dx equal to c1. And I had written in this section in a very explanatory way, because you guys may be have a problem if I do this indirectly. Okay, dt by dx in new section, if you have any problem how I find out the dt by dx equal to c1, you can, if you integrate it, and we will get the dt by dx equal to, that is temperature gradient, this value will be c1, and again we have to differentiate, integrate it with respect to x, and we will get the tx, and c1x, if you integrate it in, and plus my c2. Okay, this is the equation number 3. Applying the boundary condition, we have a boundary condition given. Okay guys, we have a boundary condition given for the b. What are the boundary condition? I have written here. You also have to write it. Okay guys, please write it. Okay, now we'll go to the applying boundary condition, minus k dt 0 at x equal to 0, the boundary condition